Let's start by taking a look at an integral that we did in class last time. So the integral of sine squared x dx. There's a couple of different ways of doing this one. The first way that I'll review is just the way we did it in class. So the idea here is just to recognize a trig identity to rewrite the sine squared. So and that's the sine squared is 1 minus cosine 2x over 2, some form of the double angle formula. Okay, so using this, I can just, let's just copy that in. I can rewrite this integral by breaking it up into two parts. I have the integral of a half, and then a half of the cosine of 2x. So that gives me these two separate integrals, the integral of 1 half dx minus half the integral of the cosine of 2x dx. The first thing is no big deal. Let's just take a look at the cosine of 2x, which we can also just eyeball, but just to make it straightforward, let's say that u is 2x and du is 2 dx. And so then this integral is just the integral of the cosine of u. Instead of a dx, instead of a du, I actually have a half of a du there, so I'll need to put in a factor of a half. Dx is half of du. And then the integral of cosine is sine, so I get half of the sine of u. And then u is actually 2x, so all told I get 1 half of the sine of 2x plus c. Okay, now putting that into what I have up there, let's erase that. Substituting that over there, this expression then becomes integral of 1 half is 1 half of x. And then I have my minus 1 half of what I've just solved, which is 1 half sine 2x, and then all that's plus c. Okay. So that's method number one of working with that integral. Alright, so if you don't remember that trig identity that we just used, there's another way to approach this, so, and that is integration by parts. So another way I can think of this is I could say, well, I'll break this up into these two pieces, one of which I'll take the derivative of, and the other I'll take the integral of. Actually, they happen to both be the same, but let's not let that bother us. So we'll let u be sine x, and the dv be sine x dx. Okay, so breaking it up like this, well, let's see what the other pieces are. So we have our du is the derivative of sine is cosine, and the v is the integral of sine, which is minus the cosine. So this is equal to uv, so that's minus sine x cosine x, minus the integral of v du. V is minus the cosine, so minus sine. Du is another cosine, so I actually have a cosine squared x dx. Okay, so I've, in some sense, like reduced this problem to a problem which is actually not very reduced. It's almost the same problem, just with a cosine instead of a sine. Now I'll do something that appears not to be useful at all, which is to switch it back into a sine. So, so cosine squared I can rewrite as 1 minus the sine squared. And now I can turn that integral into two separate integrals. So I have sine x cosine x plus the integral of just 1 dx minus the integral of sine squared x dx. And what I found here is that I am left on that far side with the original problem that I have. Let me just get rid of that last integral. So the integral of dx is just an x minus the integral of sine squared x dx. Okay, so all told, what I have is that the integral of sine squared x dx is minus sine x cosine x plus x minus the integral of sine squared x dx. This is great, because this is just what happened in that other time when we had the exponential times the trig function. We have this, this pattern that then we can merge these two parts of. So I'm going to just add this thing over to the other side, and I'll get twice what I'm looking for, twice this integral. is minus sine x cosine x plus x. Now dividing by 2, and I'm done. I've got my answer. So that just says the integral of sine squared x dx is minus 1/2. Well, let's just say it's 1/2 times minus sine x cosine x plus x plus c. Okay? Now, it looks different, this answer, than the one that we got previously using the trig identity, but actually it's the same if you use the double angle formula. You can show that these are the same answer. Now, one strategy that we were using before with integrals of trig functions was using the trig identities to convert when we had powers. Like if we had something like sine cubed x dx, then the strategy was to rewrite 2 of the sines as cosines. So I'll break this up into a sine squared and a sine. And this sine squared I can write as 1 minus the cosine squared. And now I'm ripe for a u substitution. I can make u be the cosine. Du will be minus the sine. And then I'm off and running, I'm home free. I got 1 minus u squared. The sine x dx is minus my du, so I get a minus sign in my du. And I can go ahead and do the integral, and I'm so happy. Everything just works out very well. I have a u minus 1/3 u cubed plus c. In other words, I got a minus. What's u? It's cosine of x. Minus minus is a plus 1/3 of the cosine cubed of x plus c, etc. Everything is great. So this is a very good strategy to use, and it doesn't just work with sines and cosines. So the same technique is also going to be useful for a few other kinds of trig functions as well. Let's look at this variation on that same idea. So instead of a sine cubed, I have a tan cubed. But I'm going to do the same strategy. So the point is that I can rewrite a couple of these tangents in terms of the secant. So what do we have? We have, so from sine squared plus cosine squared is 1. If we divide everything through by the cosine, we get tan squared plus 1 is the secant squared. So using that identity to rewrite the tan squared is secant squared minus 1. I get that. Okay, and now there's some hope here, and the hope is from the fact that the secant squared is the derivative of the tangent. So I might be able to do a u substitution, except this 1 is kind of in the way. So to get rid of the 1, I'm just going to break it up into 2 separate integrals. So on the one hand, I have the integral of secant squared x tan x dx, and I have minus the integral of just the tangent. Now this first integral, let me do it over here, and I'm going to write it in reverse order just because it's more suggestive, tan x secant squared x dx. For this first integral, we'll make the substitution u is the tangent, because then du is the secant squared, which is exactly what I have. This first integral is just the integral of u du. So I get 1/2 u squared plus c, and u squared is the tan squared, and that's great. Now the integral of tangent, well, for now let's just remember, as we showed before, that the integral of tangent is the natural log of the absolute value of the secant. So putting these things together, we're all set. So this first integral is this one that I did there. So I got 1/2 the tan squared x, and then minus the integral of tangent, which is the ln of the absolute value of the secant. Let's see. Okay. So this was there was a bit more. It was a bit more involved than the sine cubed, but the same original strategy, and just kind of following our nose, we can still get through it. Okay, while we're in the zone, let's do some other powers of trig functions. So we just did tan cubed. let's look at some other ones. So if we do integral of secant squared, well, that's just the tangent, because we know the derivative of tangent is secant squared. So this is just the fact in reverse. What about the integral of tangent squared? So I can rewrite tangent in terms of secant squared. So again, we have sine squared plus the cosine squared is 1. Dividing through by the cosine gives me that the tangent squared, sine over cosine is tangent, cosine over cosine is 1, and that's the secant squared. And so that tells me that the secant squared minus 1 is the tangent squared. So I can write this as secant squared minus 1. And now I can break this up into two pieces, one of which I know how to do, and the other of which I know how to do. So that's great. I get the integral of secant squared x dx minus the integral of just 1 dx. So the integral of secant squared is the tangent, and the integral of 1 is x. So the integral of the tangent squared is tan x plus c. All right, we're on a roll now. We did tan squared. Let's do tan to the fourth. Why not, right? We also did tan cubed. How about tan to the fourth? Okay, so to do tan to the fourth, I'm going to do the same strategy, which is turn some of it into secant squared. So what do we have? We'll have, as before, we have the fact that tan squared plus 1 is the secant squared. So in other words, tan squared is the secant squared minus 1. So I'm going to write this as the integral of secant squared x minus 1 tangent squared x dx. Okay, and I'm going to break this into two separate integrals. I get the integral of the secant squared x, the tangent squared of x dx, minus the integral of the tangent squared x dx. Now, we just did the tangent squared. So let's put that aside for a moment and concentrate on this first part, which is the new part. So we're looking at the integral, let me write it in reverse, of tan squared x secant squared x dx. Okay, how to approach this one? Well, the point is that secant squared is the derivative of tangent. So if I call u the tangent, then the du is going to be the secant squared. And we're just off and running because we've got a u squared du. And that gives us a 1/3 u cubed plus c. So we get 1/3 u is the tangent plus c. And then to finish it off, so that this first part we've identified with 1/3 tan cubed x. Now we just have to do the second part, which, if you recall, the strategy was to just write it as the secant squared minus 1. The secant squared gives me a tangent. The 1 gives me an x. So altogether, when I put those two things together, what I get is that this integral is equal to, so the first part is 1/3 the tan cubed of x, and the second part is the tangent plus x plus c.